This is a question on combination of a lens and a mirror. So the question is as follows. The radius of curvature of the convex face of a plano-convex lens. We have a plano-convex lens in this question. Earlier we saw a convex lens or a biconvex lens in which both the surfaces were curved and both the surfaces were convex. Right, now in this question we have a plano-convex lens with a radius of curvature 12 centimeters for the curved surface, and the lens is made of glass. So refractive index of glass is given as 1.5. The first part of the question says find the focal length. Then after this we are told that the plane face of the lens is now silvered. After the silvering, we have to solve a few more parts. The next part is at what distance from the lens will the parallel rays incident on the convex surface converge? The next part is sketch the ray diagram to locate the image when a point object is placed on the axis 20 centimeters from the lens. The last part is calculate the image distance for part C. So we are given a question in which we have a plano-convex lens to start with, and then the plane surface of the plano-convex lens is silvered. So this essentially forms a combination of a lens and a mirror, a plano-convex lens immediately followed by a plane mirror. Then for that we need to find out the focal length, and following that we need to find out this question part B says at what distance from the length will the parallel rays incident on the convex surface converge. So this is essentially this question essentially means that we are supposed to find out the focal length of the combination of the lens and the mirror, part A is just finding the focal length of the plano-convex lens. Part B is finding the focal length of the entire system in which the plane surface of the plano-convex lens is silvered. And then we need to draw some ray diagram and find the image distance for object placed at a certain distance. So let us first draw the diagram. So we have a plano-convex lens, and then later on one of its the plane surface is silvered. So let us now start solving the question. For part A, this is finding the focal length of the plano-convex lens. So we can use the formula for thin lenses. So for thin lens, the refraction formula is as follows. We have seen this earlier as well. So 1 over the focal length of the lens is equal to refractive index of the material the lens is made of with respect to the material in which the lens is submerged. Here it is air, so refractive index of glass with respect to air. Then we have a term containing the radii of curvature of the two surfaces forming the lens. So this is refraction from thin lens. So we just need to plug in the values and we will get the focal length. So let us plug in the values. Refractive index of glass we are given is 1.5. So 1.5 minus 1. R1 is the radius of curvature of the left surface and R2 is for the right surface. So the radius of curvature for the left surface we are given is 12 centimeters. And radius of curvature of plane surface is going to be infinity. It is plane surface, so a plane surface has infinite radius of curvature. And for this, according to the sign convention, this will be negative infinity. So this gives us one over infinity is simply 0. So from here we get the focal length of the lens, which comes out to be 24 centimeters. So we have solved the first part, finding the focal length of the plano-convex lens. The next part is to find the focal length when the plane surface is silvered. So we have the following setup: plano-convex lens with plane surface silvered. Now in order to solve this question, let us break it down. Let us break it down into three parts. First, we will consider the rays coming in to the plano-convex lens. We will ignore the mirror. Then we will consider the effect of the mirror. So rays are coming in, they pass through the plano-convex lens, then they hit the mirror, and then finally we will again consider the lens, because this time the rays are hitting the mirror and then again passing through the lens, going in the reverse direction because of reflection. And then finally these rays are going to converge to some point which is the focus point. So we need to find out the focal length for this kind of a system. So we have broken it down into 3 parts. So for the first part, let us look at it. For the first part, we have plane rays coming in, and by definition plane rays converge to the focal point. So plane rays which converge to a point which is at the focal length of the lens, which is nothing but 24 centimeters, as we saw in part A. So if we use the lens formula, we can even use the lens formula, and then we will see that this is indeed the case. This is our lens formula. So in this lens formula, our object is placed at infinity. U is infinity, because rather minus infinity according to the sign convention. So object is placed at infinity because we are considering parallel rays. So for such a case, when U is minus infinity, V is equal to F. From the lens formula also we get this. So the image for an object at infinity will be formed at the focal point. Now in the next part, we will consider the effect of the mirror. So the effect of the mirror is essentially just to reflect the rays backwards as it is. So if I draw the lens and the mirror, let me redraw it a little bit better. So this is the lens, the rays are coming in, they will refract, they will bend when passing through the lens, they will bend, they would be bending like this, and then immediately after that, just for exaggerating it, just for making things a little bit clear, I am drawing it far away, but immediately after that surface we have the lens, the mirror. So if the rays are coming in like this, they will get reflected by the mirror like this. So let me draw the reflected rays in a different color. So because of the mirror, the rays are going to be reflected and they will change their direction according to the laws of reflection that we have, in which the angle of incidence would be the angle of reflection. So if we draw a normal to the mirror, we will see that the angle of reflection has to be equal to the angle of reflection. So this angle right here would be the same thing as this angle of reflection. So angle between this normal and the white ray, the incident ray, is the same as angle between the normal and the red ray, which is the reflected ray. Same for the ray over here, the white ray and the red ray. So the effect of the mirror is just to reflect this. So this means that if we consider, if the mirror was not there, then the image would have been formed somewhere here at the focal point of the lens. Because the mirror is there, these rays are going to get reflected and they will meet at some point, and because of this property of plane mirrors, this distance is also going to be same as focal length of the lens. Why? Because this distance and this distance behind the mirror and distance in front of the mirror is the same by reflection from a plane mirror. This is due to reflection from plane mirror. So in a plane mirror, if I just draw the situation for a plane mirror, we all know that if object is at a certain distance d, then the image of it will also be at the same distance d. So if this is the object, if this is the object, and then the image will be formed at the same distance. In our case, what is happening is that we do not have an object in front of the mirror per se, because for our case, the rays are getting refracted by the lens and the image from the lens is being formed somewhere here. So this is like a virtual object for the lens, for the mirror, and this is the image formed by the lens. So the image formed from the lens is acting as the virtual object for the mirror. So the image from the mirror would be formed somewhere here. This is all mathematically just to simplify our problem, just a mathematical construct that we use. We treat this image from the lens as the virtual object for the mirror, and then the mirror will simply reflect it and we will get the image exactly at the same distance in front of the mirror. Now in the third part, we will add the effect of the convex lens after reflection from the mirror. So we had divided this configuration of a silvered plano convex lens as just a single plano convex lens plus a mirror plus another simple plano convex lens. So now what we have is, let me draw the situation. We have the virtual object for this second encountering of the plano convex lens. We have the virtual object for the lens. This is image from mirror, which is acting as the virtual object for the lens, and we can use, and this distance we know, this distance we know is focal length of the lens. So we can again use the thin lens formula. This time the rays are going in this direction, they will go in this direction from the lens. So they are coming in like this because of the mirror. So the rays are moving towards the left direction. So the left direction according to the sign convention is going to be positive. So if we plug in the values of U and F in this thin lens formula according to the sign convention, thin lens formula, so we will get the value of V. So let us just plug in. So U in our case is F lens, same distance. U, the object is over here. This is the virtual object for lens. and this left direction is positive. This is the direction of the rays. So we get this gives us V is equal to F length by 2, which is equal to 24 centimeter by 2, which is 12 centimeters. So this is the solution for the second part. Why is this the solution? Because we have found out the image location for an object placed at infinity, and for object placed at infinity, image location is the focal plane. That is the definition. So object placed at infinity, image is at focus. So this is how we find the focal plane of a lens, by placing an object at infinity or very far away from the lens, and where we get the clear image of the sharpest, clearest image of that object, that is the focal plane of the lens. So we have found out the value of the focal length of the plano-convex, silvered plano-convex lens. So focal plane of the entire system, focal plane of silvered lens is 12 centimeters. Now there is another way in which we could have tackled this question. This is a simpler trick to solve this question. So let me write down the simpler trick. It is based on all of this maths that we have done, by finding out the images for each of the components, and those images will act as the virtual objects for the next subsequent components. So based on this only, we have a trick which can be used to solve the question much more easily. So we have power of a lens, defined as the reciprocal of its focal length, and power of combination of thin lenses placed one after the other, so power of the combination is simply sum of the power of the individual terms, whatever the individual components are: convex lens, concave lens, plano-convex, plano-concave, whatever we have. So power of the combination of lenses is given as follows, and power of just a single lens is reciprocal of the focal length. Now how would we solve this question using this? Well, we note that in our combination, as we had decomposed it over here, in our combination we have one lens followed by a mirror, followed by the lens again, because the ray passes through the lens once again. So our combination is essentially lens, let me redraw it properly, lens plus mirror plus the lens again. So this is our combination. So the power of our combination is going to be power of lens plus power of mirror plus power of lens. So this is power 2 times power of lens, 2 times power of lens plus power of mirror. So this is 2 times power of lens is 1 over focal length of the lens, and power of mirror is 1 over focal length of the mirror. Now focal length of the mirror is infinity, because in a mirror, if rays come from infinity, they will get reflected and they will go back parallel. So parallelly, and they will meet at infinity. So focal length of a mirror is infinity. So we have 2 by f lens plus 1 over infinity, which is 1 over infinity is 0. So we have simply this, which implies, and the combination is silvered plano convex, and this f combo is basically f silvered lens. So this gives us which is nothing but 24 centimeters by 2, which is 12 centimeters. This is same as what we had obtained by the other method. We had obtained the same value, 12 centimeters over here, same 12 centimeters over here. So this is another trick that one can use to solve questions much faster. This is essentially based on this thin lens formula that we have, and repeatedly applying the thin lens formula, we get this power of combination of lenses, and this we can apply to our given combination by breaking it down into individual components. So this solves the second part. The third part says that we need to sketch the ray diagram. Ray diagram for an object placed 20 centimeters from the lens. So let us draw it. This is parts, sorry, I need to change the color. So this is part C. So we know that the focal point of this is 12 centimeters. We just found out in the previous part, and the object is being placed at 20 centimeters. Let me shift this thing. So this is where we are placing our object. So this is object, and this is 20 centimeters. We need to draw the ray diagram. So we will draw a ray. The ray will encounter the glass surface and then it will bend. So if we draw a normal, then the ray will bend inside and then the ray will get reflected from the mirror. Let me redraw it. This is getting a little bit congested. So I think I should draw a magnified lens for magnified version of this so that the diagram is clear. So if we draw so we have an object which is beyond the focus. So if ray goes horizontally, then it will simply come back, reflect and come back horizontally. But if ray goes at some angle, then we draw a normal to the surface. The ray will bend towards the normal because glass is an optically denser medium, so the ray will pass through the lens like this. Then for the mirror, again we will draw the normal. For mirror, it will just reflect it. Angle of incidence is same as angle of reflection, so mirror will reflect it. Then we come here, then we'll again draw normal at this point, and since it is coming from a denser medium to a rarer medium, the ray will bend away from the normal, and will go and intersect the horizontal axis at some point over here. So this is going to be our image point if this was the object. So this is still looking a little bit cluttered. If I can identify the rays for you. So this white ray right here is the incident ray from the object inside the glass. Let me use a different color. Inside the glass, after refraction from the glass surface, it takes this blue line. Then after reflection from the mirror, it goes along this purple line. And then finally, after another refraction from the curved surface, it follows this red line and intersects somewhere over there. And the horizontal ray coming from here would just go back, trace its path back, and then these rays will intersect at this point, which is the image of the object. So this is the ray diagram. In the next part, we are supposed to find out this image distance. We are supposed to find out this distance. So let us do that. Before doing that, we note that our combination, this plano convex lens, plano convex lens plus mirror, this combination effectively acts as a concave mirror with focal length equal to the focal length of the silvered lens, the focal length of the combination that we found out in the in part B. So this focal length of silvered lens, this is the effective focal length of this system. So this system is behaving like a concave mirror with this effective focal length. Why am I saying so? Is because the rays are getting reflected. So the rays are coming in from here, and then they are getting reflected, and then they are moving back and forming image on the same side as that of the incidence. So this is like some sort of a concave mirror configuration. So we will use the mirror formula here. the mirror formula says that 1 by f is equal to 1 by v plus 1 by u. This is the mirror formula. And then we can plug in the values. We have f is 1 over f silvered length is equal to 1 by v plus v we need to find out, and the object distance is u we are given is 20 centimeters from the plane surface, and according to the sign convention, so the rays are moving incident towards the right, so this will be the positive direction measured from the plane surface. This is the pole, so measured from here. So according to the sign convention, left side is going to be negative, so left of the pole means this direction is going to be negative. So object distance is minus 20 centimeters. So this gives us, and focal length is also negative, minus 12 centimeters. We found out the value, the magnitude as 12 centimeters. So this is that, and then we can find out v. We can solve this. This gives us v is equal to negative 30 centimeters. So this solves the question. This image distance, so this distance right here is 30 centimeters. So if object is at 20 centimeters, this is the object distance, then the image is at 30 centimeters. So the important takeaway from this question is this combination, the combination of different optical elements. So the power of combination of different optical lenses is simply the sum of the power of the individual elements. So if we are given a combination of optical elements, we can use the thin lens formula or the mirror formula subsequently and then solve the question like we did. So we divided our optical element into 3 parts and then applied the lens or the mirror formula accordingly to each of the parts and finally obtained the image distance, or we could use this combination to quickly find out the focal length. And then using that focal length, we can use the lens or the mirror formula and solve the question.